All right, in this video, what we're going to do is spend a little bit of time practicing drawing these molecular compounds based on what we've learned so far. And again, these are called Lewis dot structures for these molecules, okay? So just as a quick reminder, I'm going to put the periodic table over here. Remember, the valence electrons is all determined by what column the element is in. So you have to know these. Okay, so the first one we have over here is HF. So HF, called hydrogen fluoride, or hydrogen monofluoride, or actually hydrofluoric acid is what it's actually called. We're going to have one dot for the hydrogen. I'm going to automatically point it towards the F because I'm going to know I'm going to need to bond with it. So there's no point in pointing to the left, to top, or bottom. I might as well point it towards the fluorine because it's going to be in a bond. Fluorine, again, is in the seventh column. It's a halogen. I'm going to go ahead and put one pointed towards the hydrogen because, again, it's going to have to bond. And then I have six more. So there's 1, 2, 3, 4, 5, 6, plus the seventh on the inside. I'm going to bond. And again, that's all there is to it. So fluorine has its 7 dots. Hydrogen has its 1 dot. And then they're going to share. So the hydrogen will get one more to make 2. Fluorine will get one more to make 8. So that's one of the most simple compounds you could draw. Again, that's hydrogen monofluoride, or actually hydrofluoric acid. All right, excuse me, the next one, H2O. Again, we have 2 hydrogens and 1 oxygen, so clearly the oxygen is going to go in the middle. We're going to have a hydrogen on either side. Again, hydrogen in the very first column, so it gets 1 dot. I'm going to face it towards the oxygen again because I'm going to have to make a bond, right? Oxygen, again, is in the 6th column, so I'm going to put 1 facing each hydrogen, and then that's 1, 2, and I have 4 more. So I'm going to put those in pairs, like so. And there we go. That, again, is what water is going to look like. Not exactly, it's actually a bent shape, not a linear shape, but we'll get to that. But right now, again, we have our 8 right here for the oxygen, and then we have the 2 right here for each of the hydrogens. All right, the next one, again, we've seen this one before. We have 1 carbon and 4 hydrogens. Again, remember, this is called methane, or carbon tetrahydride. I'm going to point one of the 4 dots towards each hydrogen, and the hydrogen each gets 1 dot because it's in the first column. I'm going to bond those together. Again, here's each of the ones for the hydrogen. And then, of course, there's the 8 for the carbon. Okay, let me make sure that's connected. All right, the next one we have is called ammonia, or nitrogen trihydride, but really its name is ammonia. So we're going to have a nitrogen in the middle because there's only one of them, and we're going to have 3 H's. Okay, you already know H's get 1 dot. I'm going to face it towards the nitrogen. Nitrogen, again, is in the 5th column, so I'm going to put 1 facing each hydrogen, so that's 3. And then I have an extra pair. Remember, you always end up with pairs. Just to remind you, if you have any extra electrons, they're always going to be in pairs, right? Never by themselves. I'm going to go ahead and bond these together. And there we go. So that's what ammonia is going to look like. Again, just so you guys can see it. Here are the 8 for the nitrogen, the 5 it contributed, plus the 3 from each of the hydrogens. And of course, the hydrogens each get 2. Okay. The next one we have is carbon dioxide. Again, we already drew this one, so we have a C. Let me go ahead and keep the same color. Carbon in the middle, we have an oxygen on either side because there's 2 of them. Again, we're going to put 1 facing each oxygen because they're going to have to bond. There gets 4. Each oxygen, again, gets 6. So I'm going to face 1 towards the carbon. I'm going to then put, there's 4, 5, and I'm going to double them up, 6. 1, 2, 3, 4, 5, 6. Now, again, if I bond this, we already know from the previous video that that's not going to work. Clue is that we have individual electrons. That right there, again, is a red flag, and that should tell you that this is not the correct form. Remember, we will have doubles or pairs, but we will never, ever, ever have singles all by themselves. So that tells me what I need to do is move this one and this one. I'm going to put them, move that one there and that one there. So there we go, a double bond. I'm going to move this one over here and this one over there. So now I'm going to move that one there. It still has its 6. I'm going to move this one here so it still has its 4. It looks a little sloppy, but there you go. There's carbon dioxide. Again, just so you can see it, here are the 8 for the carbon. The 2 on the center, these are the original ones. These are the ones that are contributed from the oxygens. And then again, here are the ones, the 8 for the oxygen. Each has 6 plus 2 that it's sharing. Therefore, it has 8. All atoms there have 8. Okay, it's kind of like puzzles, right? In 2, again, we've already done this one as well. Again, we call this not dinitride, but it is nitrogen. We have a double bond here, and then we're left with 1, 2. Actually, it's a triple bond, isn't it? There we go. Again, because there's 1, 2, 3, 4, 5. This one has 1, 2, 3, 4, 5. Again, just so you guys can visualize it, here are the 8 for that nitrogen. Here are the 8 for that nitrogen. It is like a Venn diagram if you think about it, because the ones in the middle are shared, which is what a Venn diagram is all about, right? And that, again, in essence, is what a covalent bond is all about. All right, the next one we have is BF3. Again, we would say that is boron trifluoride. So there's only one boron, so clearly it goes in the middle. And then we have 3 fluorines. So I'm going to put those in different directions. Boron, again, has 4 valence electrons. 1, 2, 3, 4. This is interesting. 1, 2, 3, 4, 5, 6, 7. You already know fluorine gets 7, right? So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So that's interesting. That would actually be a resonance structure, which is going to be a little bit weird. I'm going to talk about something like this a little bit later, because that is an exception. Again, the exception is this issue right there. That's the problem. So we're going to do an exception here in a little bit, but for now, I don't want to confuse you guys with the exceptions before we get through the rules. All right, the next one we have is HCl. That is, you could call it hydrogen monochloride, but really it's hydrochloric acid. We have an H, oops. We have an H and a chlorine. Okay, so H again always gets 1. Chlorine is a halogen, so it gets 7. 1, 2, 3, 4, 5, 6, 7. Bond those together. So chlorine has 7, it's getting its 8th. Hydrogen has 1, it's getting its 2nd. Again, not surprisingly, these two look identical because, again, fluorine is the same family as chlorine, so they're going to bond the same way with hydrogen. So again, that shouldn't be surprising that they look identical because, again, with the same number of valence electrons, of course they're going to look the same. All right, SiO2. Si in the middle because there's only one of them. We have 2 oxygens, so I'm going to go ahead and put them on either side. Silicon is underneath carbon, so it gets 4 dots. 1, 2, 3, 4. Oxygen, you guys should already know, gets 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Again, you should already be noticing this is a problem, that's a problem, right? So what that tells me again is I need to start moving some things. I'm going to move this one over here. I'm going to move this one down there. So then I'm going to relocate that one there, relocate that one there. Then again, I'm going to go ahead and put this one up here and this one over there. So let me erase that temporarily. I'm going to replace them. Here's that one, here's this one. And again, there we go. Notice again, these look identical, which again, should not be surprising. Carbon and silicon both have 4 valence electrons. So they're going to bond with oxygen in a identical way because that's how the chemistry works. With the same number of valence electrons, again, they're going to behave very, very similar. Now, the next one is a really cool one. This is HCN. HCN is cyanide. Cyanide, of course, is highly poisonous. HCN. So what we have is hydrogen, carbon, and nitrogen. We don't call that hydrogen monocarbon mononitride. It's just cyanide. So there's one of each. So I'm going to go ahead and put the C in the middle. It's going to be in the correct order. Hydrogen gets 1, carbon gets 4, face 1 towards each element. Okay, nitrogen gets 5, 1, 2, 3, 4, 5. Notice I'm doubling them up. Okay, so I'm going to bond. Okay, so does that work? Hydrogen brings us 1, gets 1 more, so hydrogen's happy, it gets 2. Carbon brought its 4, it's getting a 5th and a 6th, so that's not good. Nitrogen brought its 5, it's getting 1 more to get 6. So that again is a problem. Another problem, this again should be a red flag. That should point out something that's not right. So I'm going to take those two and I'm going to relocate them. Oops. I'm going to relocate that there and relocate that there. So just to get to see what I did, notice I still have the 4 from the carbon. All I've done is I've moved them. I haven't randomly added them or done anything crazy. I just relocated them. What I'm going to do next is I'm going to do the same thing with 2 from the nitrogen. 1, 2, bond. Okay, now does that work? That looks really weird, right? But does it work? Okay, so again, we already know that the hydrogen's happy. Does this equal 8? So we have the 4, 1, 2, 3, 4 from the carbon. We have a 5th, a 6th, 7th, and an 8th. So carbon's happy, hydrogen's happy. What about, let me change colors because this is getting a little chaotic. What about nitrogen? So we have it's 1, it's 2, it's 3, it's 4, it's 5 original, 6, 7, 8. Nitrogen's happy. All right, so that's the only way to draw cyanide, which again is a really weird looking molecule. Normally, just to clean this up, I would move those two just to be technical. To be correct, I would move them over here. They would really want to be as far apart as possible. Notice how I did the same thing over here. These are pointed away. Again, that's not a coincidence. Notice these again are pointing away. That again is the way that these would be drawn. Oops, and I just realized I needed to take this away. Oop, gone. All right, the next one we have is CH3OH. What this is called is methanol. It's an alcohol made of a methyl group like this, but with an alcohol stuck to it, which is the OH. So again, carbon is always going to be in the middle. If there's a carbon, it's always going to be in the middle. We have an H, an H, an H. There's the 3 H's, an O, and an H. C, H3OH. So again, hydrogen gets 1. Here's 1 for each hydrogen. Carbon gets 4. 1, 2, 3. Sorry, I'm going to kind of have to squeeze this. Oxygen again gets 6. So I'm going to point 1 towards the carbon, 1 towards the H. That's 2, 3, 4, 5, 6. Okay, this is looking good because I don't see any that are individual by themselves. There we have that. I'm going to go ahead and bond that. Let's see if that works. Let's see, does that make sense? So here are the 8 for carbon, the 4 right here that came from the carbon, and then the 4 in blue came from the oxygen and the 3 hydrogens. So carbon's happy. We already know, again, or should know, just by looking at this, that the hydrogen's happy, again, content. Okay, so the hydrogens are happy. The only thing we need to ask about is what about the oxygen? So if I circle this, you'll notice that the oxygen does get its 6. 1, 2, 3, 4, 5, 6, plus 7 and 8. So the oxygen's happy. So that looks chaotic, but that is what methanol would look like. And I'm going to erase those because we don't really need those. I just do that so again, so you could visualize where all the electrons are going. So that's methanol. Hydrogen single bond in each direction, then an O, and then an H. And I accidentally erased something, so let me just fix that before you get confused. There you go. All right, the last example we have is CHCl3. This is called chloroform. Oh, you guys have probably heard of chloroform. All right, so carbon's in the middle. If there's carbon, again, it's always in the middle. Then I'm going to have an H over on one side. It doesn't matter which side you put it on. I'm going to have a Cl, and a Cl. There's 3 Cls, 1 H. If you put the H on the top, it doesn't make any difference. Again, when it comes to molecules, there is no real top. I'm going to put a 1 for the H. Carbon gets 4. Again, you should start memorizing this by now. Chlorine, of course, is a halogen, so it gets 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. Again, I can't do the bottom two because they're off the screen. 1, 2, 3, 4, 5, 6, 7. Bond, 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 and bond. Again, do we all have what we need? Hydrogen has 2. Chlorine has 8. Chlorine has 8. Chlorine has 8. Again, the question is, does carbon get 8? Yes, it does. So there are the 8 from carbon, the 8 from each chlorine, and then of course the 2 for our friendly hydrogen. So that's what chloroform looks like. All right, guys, so that's the practice of drawing the Lewis dot structures for various covalent molecules. Again, this does not include the exceptions. Again, this is the exception, one of the exceptions right here. And I'm about to go over some other ones in the next short video. Thanks for watching.